Welcome everyone to episode 20 of Games with Go, where we will be saving our abstract picture trees to a text file and then parsing it back in and being able to load it back into from a text file into an abstract picture tree and render it again. So for a while now we've been able to take our picture trees and output them in text form. And we've used this Lisp-like syntax, which is very easy to parse. That's one of the main reasons we used it. And so what we're going to be able to do is save this to a text file, which will let us save pictures we really like, and it'll also let us be able to edit this by hand if we wanted to. Like maybe you liked the picture except you wanted more red in it, you could go in here and edit it by hand and then load it up and see how it looks. And this is going to be a cool episode because once you understand how to do parsing and how to work with abstract syntax trees, which we've been doing already, you're well on your way to being able to do things like create your own programming language or your own scripting language. And that lets you, it's pretty empowering. So this is going to be cool stuff. So first step is we need to actually save this to a file so we can load it up again. So the way we're going to do that is we're going to say if you've loaded up a large image like this and you want to save it, we'll just hit S, and that's going to save it to a file. So first thing we're going to need to do, before we start that, there was a bug I noticed after yesterday's episode, or after the last episode, in the lerp operation. Two things. One, the type for op lerp at some point got separated from the rest of its functions. So just to organize it better, let's cut the op lerp type and put it down here with the other lerp functions. And the bug is here when we're printing it, we are not printing it properly. That should be 0, 1, and 2 so that we print all of its children. Yeah, I think that was it. Is eval correct? Yeah, eval's correct. Okay. I guess one other note. The homework ideas I had, if anyone tried number 2, I think number 2 is actually impossible. Or it would require passing an array, a new array for every node, which wouldn't be faster. So don't do that one if you haven't already. Okay, so saving our pictures. Let's go down to our main function where we get the keyboard state. So we're getting the keyboard state right here, and the only thing we're using that for is to detect if someone's hit escape to close it. To save, we want to also have the previous keyboard state so we can see if someone has pressed the S key and then let go. Otherwise, pressing the S key is going to fire lots of times and save the thing lots of times, so we don't want to do that. So just like we keep track of the previous state for the mouse, we're going to do it with the keyboard as well. And we need to actually make a new array of bytes. I think this is an array of bytes. Oh, uint8s, which is the same thing, I think. And this should be the same length as keyboard state, and then we're just going to copy it. So we'll loop through the keyboard state. Oh, we can just say V. That's quicker. And then we'll bring this loop down to the end of our game loop. And copy it there so that at the beginning of each loop we'll have the previous state here, and then SDL manages the keyboard state array, and it's going to update it right here when we call poll event. Okay, so now we can detect the S key being pressed and then let go. And so we're going to want to check for that in the zoom state. So zoom state's here. So we're going to say if keyboard state scan code S is not being pressed and previous keyboard state is being pressed, then we're going to want to save. So let's make a function for saving. And the other thing we'll need is our zoom state to also have a copy of the tree associated with the image, because we don't right now. So let's go up to the top and add a zoom tree. Which will point to a picture. And then here we'll set it. This is inside of our loop where we check for right clicks. We'll say state.zoomTree equals pictrees of I. And we don't need to print it anymore. We're about to save it. Okay. So now we're going to make a function to, we need to, when we set the state the first time, give a nil for the picture tree as well. Okay, now we'll do our save function, which will accept a picture tree. And we got to save it to disk, which we've never done any writing to disk before, I don't think. So let's do it now. We're going to need a package called IO import or IO util. And that is imported like so, IO/IO util. We're also going to end up needing the OS package. Let's go back down to save tree. Okay, so we need to have some scheme for saving this. We're not going to pop up a file dialog and ask for a file name at this point. So what we'll do is we'll just say that the first time you save an image, it's going to save it as 1.apt for abstract picture tree. And the second time, it'll be 2. And so on. And we can actually look in the file system and see like what the biggest apt is saved so far, and just save it with 1 plus that. So to do that, we need to get a list of all the files in the current directory, and that's pretty easy. So as always, check for errors. And we'll say the biggest number we have so far is 0. And then we'll iterate through all of the files. All right, this files is an array of file infos. And one of the things you can get from a file info is its name. So that's the file name. And we'll check to see if, we need a new class here, so a new package to import. There's a package strings, which has some handy string utilities. So we'll say if strings dot has suffix. So what this does is you give it a string, or file name, and a suffix you want to check for. And it'll check to see if this string ends with this string. So if it has the suffix, then we want to see what number is in front of it. So we'll say number is strings.trim suffix. Number. And what this will tell us is this will give us a string that has this suffix removed from the end of it. Okay, so this will give us everything before the .apt. And then we want to take that string, let's call this number string, and try to turn it into an integer. And again, we'll have to import a package. Go back to the top. There's a package called string conversion, which has handy string conversion functions. So we'll call string conversion.a to I, which converts a string into an integer, or errors if it can't convert the string into an integer. So if error is not equal to nil, let's say if error is nil, so if there was not an error, then if the number we got is bigger than the biggest number so far, biggest number equals that number. Suffix with an X. Okay, so what this is going to do is go through all the files in the current directory, check each of them to see if they're APT files, get the text that precedes the file extension, try to convert it to a number. If it is a number, check to see if it's bigger than the biggest number we've had so far. So at the end of this, we'll get the biggest number. And if there is an error, if someone has a non-numerical .apt, it's just going to ignore it, and that'll be fine. Okay, so now that we have our biggest number, we can make our save name. And we'll use string convert again and go backwards this time. We'll go I to A, which turns a number into a string. And we'll take the biggest number plus 1, and then we'll add .apt to the end. And then we need to create that file. And for that, you can call os.create and give it the file name. And that's going to create a file handle for us. And again, check for error. And we'll use defer to make sure that file gets closed. And then to write to that file, we can call fprintf, which is like the print line functions we've been using, but we'll write to a file instead of to the console. So we give it the file handle, and then we just call p.string, which is a function we already have that turns picture trees into this string we see down here. So that will get written to a file instead of the console when we save. All right, so that should all work now if we haven't made any mistakes. So let's try it. So we'll pick an image we like, maybe this one. And we'll hit S. And here we go. You can see it. If you have VS Code, you can see the new file. If not, you can close the program and list the directory. So we've got 1.apt, and we've got our string there. All right, so that's the easy step, saving it to file. Now we need to be able to parse this and turn it back into an actual data structure. And we want to make it flexible enough that we can, have spaces in here, or carriage returns, or tabs, and have it all still work, right? We don't want it to be too picky and have to look exactly like we output it. Because if humans edit it, they might introduce different spacing and stuff, and that should be okay. Okay, so the job of parsing stuff from text files into data structures is pretty tricky. The way there's various approaches to doing it. What some people do is use external tools where you can describe your language in a special language of its own, and then the program will output a parser for you. We're going to do it by hand because the point of this stream is to learn. So first thing we're going to do, we're going to have a bunch of functions for doing the parsing, and we're going to keep it part of the abstract picture tree package because it naturally goes along with it. It's going to be using it. It's going to be building an abstract picture tree. But we can organize things by creating a new file in our APT folder. Right, we can give it a new name, but we can still put package APT at the top, and then it'll be as if these were all in the same file as far as the compiler is concerned, but it may be a little bit better organized as far as we, the humans, are concerned. So this is just one option you have when organizing your code. If a package starts getting huge and you start having a hard time finding stuff, then you can split it up into multiple files, however you want. So we're going to do that. We're going to put all the parsing related stuff in here. Okay, so parsing is usually broken up into 2 steps. Step 1 is called Lexing. And what Lexing does is take the raw text you have that might look something like this and break it up into tokens, where each token is one logical unit that you're interested in the text file. So in this case, our the kind of things we're interested in are things like the parens. We're going to want to see all the paren characters, open and close. We're going to want to see all the operator names, like lerp and plus, divide, simplex noise, right? We're going to want to have those all grouped together. And we're going to want to see the x's and the y's and the numbers, right? Like we've got those constant floating point numbers in there. And so the idea of Lexing is to take your messy text file and turn it into just a list of these logical units, right? So this would be like an array or a linked list, just one after another. And that helps break up the problem of parsing, which can be really, it can seem daunting. So instead of having to worry about it all at once, first step, all you worry about is just how do I break up this text into a list of things I'm interested in, right? And if your language had comments or something, you could ignore those and not even bother putting them in your list of Lexed things. And you ignore all the white space, you ignore the tabs, you ignore the carriage returns, unless those are important to your language. Okay, so how do we do that? How do we do the Lexing? So when you're going through these files, you typically are going in different states. Like at the beginning, you might be looking for your first open paren. And after you've found an open paren, then you're looking for an operator. And after you've looked at an operator, you may be looking for an open paren again, and so on. If you see a number, then you need to start going into a state where you're reading in a floating point number. So you're transitioning from one state to another based on what you find in the file as you go along through it. And that concept is known as a state machine. So often you want to create some kind of state machine where you can easily transition from one state to another as you find new things in the text file. So one clever way to do that, which I have completely ripped off from Rob Pike, who has a great talk on how to do Lexing on YouTube. I'll put this link into chat. You can watch this later. He explains it really well, and our Lexer is going to look a whole lot like this. A little different, but not much. So this all comes from him, the Lexing part. The parsing we'll have to do on our own after that, but it's not hard. So the basic idea starts with this. You have a state function, which is a function that takes in a Lexer, and I'll show you what that is in a minute, and it returns another state function. So I don't think we've seen this before in the stream, but we are creating a new type called state function, and that type is a function. You can do that. You can make types that are functions. And it's a function that has to take in a pointer to a Lexer, and it has to return another state function. So we can make multiple functions that are state functions, right? Like this would be these would both be state functions because they both take in Lexers and return different state functions. You just have to satisfy the signature defined here, and that means you are a state function. So that's the heart of it. So what is a Lexer? The Lexer is just a data structure that basically keeps track of where we are in the text. So we're going to have our input, which is a string, and that'll just be the entirety of the file we're loading in this case. We're going to have the current start position in this input string of the current token. So whatever token we're working on, start will point to the beginning of it in the input string, right? So if we see a number, right, start's going to be like right here, and when we get done, start will still be right there, then we go to the next token. Position will be the actual character we're pointed at the moment in the string. Right, so we're going to tend to keep incrementing that by 1 to look at the next character over and over. Occasionally you might want to back up too. Width is the width of the current character that we're looking at. We're going to be supporting Unicode, which means some characters are multiple bytes, and width will let us keep track of that. And then we're going to have our tokens, which is going to be a channel. And this is going to be cool because what we're going to do is as we get tokens, instead of just putting them into a list and waiting till we're done to begin parsing the tokens into an abstract syntax tree, we can actually have the Lexer running on a separate thread or a separate Go routine, spitting out tokens as it gets them, and the parser can start parsing on another thread at the same time. And it turns out you can do that without even making the thing any more complicated than it would be. Like you get free multi-threading to some degree. Obviously that's not a big deal for files this small, but it's fun that we can do that. Okay, so what is a token? This is a very typical structure for a token. You're going to have some kind of type indicator. Right? Is it an open paren? Is it a function name? Is it a number? And so on. And then a value, which is a string. So for instance, we might call all of the operators, we might call these operator, and then the string, the value we're going to put in here would be the actual name of the operator we found. So when we have our list of tokens, we're going to know exactly what everything is and exactly what string it contains. So that will make the final parsing step much easier. So a token type is just going to be an enum, and enums are a little bit bizarre to define in Go. First you make a type alias for an int, so token types will be ints. Then you make a series of constants, and then you use the magical iota to say that you want this to be 0, the next one to be 1, the next one to be 2, and so on. So open paren, we're going to have close parens, our operators, and our constants. Constants are going to be different than all of our other operators because we have to parse them as numbers, so we're going to keep track of them separately. Okay, this is the basic structure. How are we going to kick it all off? Let's make a function, we'll call it begin Lexing, and it'll take in the entire file as a string. And when it's done, it's going to return a node, because the Lexer is also going to kick off the parser at the same time, and when everything's done, we'll get back a node. So let's make our Lexer object. So the input we have, it's an S, we're going to initialize our tokens. So I don't know if I've shown this syntax very often for structs, but if you don't want to have to provide all of them in order, you can provide the name, colon, and then the value. So we're not going to provide all of them. A lot of these are just going to be 0, so we don't have to bother. So tokens we need to initialize. We need to make a channel. It'll be a channel of tokens, and we're going to make it a buffered channel. I'm just going to give it 1,000. That might be overkill. There, we give it 100. It doesn't matter much. What this means is that the Lexer can keep putting tokens into the channel even if the parser hasn't pulled them out yet. If you did not make this buffered, then once the Lexer put something in the channel, it would pause before it could put another one in until the parser had taken it out. So by buffering it, the Lexer can keep zooming along even if the parser were lagging behind. Okay, then we're going to have a run function for our Lexer. So this will be a function attached to the Lexer called run. And this is kind of where the magic happens. So we're going to say for state, so we've got kind of a magic loop here. What the loop does is it sets state equal to some starting state function we're going to give it, right? One of these. And it's going to keep looping as long as state is not equal to nil. And each time through the loop, state is going to equal the state it gets back from the current state when we pass in the current Lexer. So this is how we go from one state to another, right? So if we start this with a state function that's looking for an open paren, then when that completes, it's going to return a new state, which might be looking for an operator. And it's going to go again. And when that's done, it might be looking for a paren again, and so on. So we need to figure out what the that first something is. So we're going to make our first state function. Oh, and when we're all done with the loop, we are going to close the channel. So let's make our first state function. So this will be one that basically starts looking for the first token to grab. So I'm going to call it determine token. It takes in a Lexer and returns a new state function. This is going to loop, and each time through the loop we want to grab the next character in the string, see what it is, and decide what to do with it. So in order to grab the next function, or our next character, we want to have some helper functions. So we're going to do a whole series of helper functions here. Break this hard problem up into lots of small, easy problems. First will be next. This will be built onto the Lexer. Lexer is our receiver. And it's going to return a rune. A rune is a Go type that just defines a Unicode character. It could be a multi-byte character. So we're going to look to see if the current position in our Lexer is greater than the length of the input. So if we try to call next, and we're now past the end of the file, we'll set the width to 0 and return EOF. And EOF we're going to define, we haven't defined that yet, just as -1. And that will be our special signal that we're done with the whole file. Okay, otherwise, we want to get the current character. So there's a special package, UTF-8. We'll need to import that. Let's do that now. Let's see, how do we get that? It's Unicode / UTF-8. So we'll call UTF-8 decode rune in string. We're going to give it a string. Give it a slice of our string that starts at the current position of the Lexer. All right, so we're taking our string and getting a slice that goes from the current position to the end, and decode rune in string gets the next rune in that input, which might be multiple bytes in that string. And it also returns the width of that rune. So we're setting the width and then getting the rune, getting the character. And then we need to update the position by adding the width that we just got. And they're going to return that rune. Okay, so now we've got a function we can call to easily get the next character, which updates our Lexer when we do it. Something else we might want is the ability to back up. Sometimes you try the next character, it's not what you expected, so you need to back up and do something else. So you back up by the width of the current rune. Another function we're going to want is an ignore function. So this is how you can like go further along in the input without actually storing anything. This is what you might do with white space characters, for instance. So we update the start position of the current rune to the current position, right? Because we're not going to take the current stuff we're looking at as part of the next token. It's just, we're just skipping it. And finally, for now, we're going to have a peek. Which lets you look at the current character without advancing the Lexer. So we're going to use that same decode root and string. But without doing all of this updating of the position. Okay, that's a good start. Let's go back to our determine token function. So we're going to use a switch statement and say r is equal to l.next. So we're getting the next rune, and we want to look at what it is. So let's think about the possible things it could be. It could be white space. It could be an open paren. Could be a closed paren. Could be start of a number. It could be the end of a file. Or it could be it could be an operator, right? It could be the next thing we find as an operator, whether we think it's going to be an operator. So we need some more helper functions again. So we need to check, be able to check to see if a rune character is white space. Open paren and closed paren are easy. That does it right there. We also need to check if something is a number. So let's do the white space and number helper functions. So white space should be pretty easy. We'll just say func is white space, takes in a rune, returns a bool. And we just need to check 3 cases that I know of. Maybe 4. So this would be a space, a new line, and a tab. And maybe we should also check for carriage return. Is that a /R? So maybe we look for that too. All right, so these are all characters that are white space that we just want to ignore. And is a white space will tell us if that's what we've got. And then the other one we might want is whether we are a number. And for that, we want to check if R is greater than or equal to the 0 character, and R is less than or equal to the 9 character, or R is a minus, or R is a plus. So if we see a character that is a 0 through 9, or a minus or a plus, then we might be looking at a number. So that gives us those. So if we imagine we're going through this, we're looking to see if we have white space and we skip it. We're looking to see if we have parens. And we're looking to see if we have the starts of numbers. So we can pretty much assume that if we have not found any of these things, or an end of file, that we must be reading in an operator. Because that's all our language has, right? It's got operators, parens, and numbers. So we can assume that if we haven't found any of these, then we're reading in an operator. That has to be an op. Okay, so what do we do in each of these cases? The white space case is easy. We just ignore it. Oh, okay, chat asked, what about a dot for is number of floating points? Good question. We should probably rename this. I guess it's possible that a human could enter a floating point number like this. So yeah, you're right. We should allow a dot. So we'll say R equals dot to check for numbers. I'm still going to call it is start of number because that's really what we're looking at. Okay, so white space. We use our handy ignore function, which will advance the start pointer in the Lexer. In the case of R, we're ready to actually spit out a token. So let's make another helper function to spit out tokens. And we're going to call that emit. Emit will tell the Lexer, go ahead and spit out a token. So that's going to take a token type and spit one out. So we're going to take the tokens channel and write to it a new token. We'll say the token type is whatever we pass in. Then we take a slice of the input from the start integer to the position integer. And then we'll update our start to the position. Because we're emitting a token, so we're going to move on to the next one. And something interesting to note here, the way we're using these slices of the string, is that like these tokens don't actually have a separate string. They're just pointing to a region of our original input string. So we're not actually making any copies of that data at all. So it's really good with memory. We're just passing around slices of the strings. We're not making any copies, which is especially good when you're working with garbage collection because you don't want to allocate memory because then you have to collect it. Okay, so that can emit. So to handle this, we just l.emit open paren. And here we just l.emit close paren. Simple. Okay, is start of number. is harder because now we have to parse a number. So this is going to be our first time when we have a new state function. So we're going to want to lex a number. So we're going to return a new state function. We don't call it. We just return the state function that needs to run next, and this loop is going to run it. So let's go ahead and set this starting starting token, right? So you notice we're only giving it the name of the function here, right? That's our function pointer, and it gets called here. So the first state function that'll get called is determine token. If it sees a number in the input, it's going to return a new state function. So that'll get set here, go through the loop again, call it again. So we're going to need a lex number function. Lex Luther function. Okay, so how do we do this? So we're going to need some new helper functions. We're going to call them accept and accept run. And they're going to take in a string, return a bool. So what does this do? It oh, that's right. Oh, strings. We need to import strings. Let's go to the top. Strings plural. Okay. It takes a string of characters and checks to see if the next character in the Lexer exists in the string we passed in. If it does, it returns true. If it doesn't, it backs up, because remember it just called next. So if it doesn't exist, it backs up and returns false. So it's a way to say, is the next input one of these things or not? So we can say something like this. We can say L.accept plus, minus, or decimal point. And what that'll do is if there is a plus, minus, or decimal point, it will pull it in to the current token and advance the position pointer. If not, it doesn't. It stays where it is. Then we can say digits. 1, 2, 3, 4, 5, 6, 7, 8, 9. And now what we want is something like accept. So we're going to copy accept. We want it to accept sort of multiple times in a row. Like here we're just looking to see if it started with a plus, minus, or a period. Now we want to pull in all the digits we find. So however many times we can call next and keep getting one of these digits, we want to keep accepting. So to do that, we just turn this into a for loop. And this does not return a Boolean. It returns nothing. So it's going to keep advancing through the Lexer, next, 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 as long as it exists in the string of valid characters. And once it doesn't, we break out and back up. So the first character that's not part of the number, we put it back on the Lexer. So now we can call except run on our digits. Now, because this could be a floating point number, once we've run out of digits to accept, then we will want to see if we can accept a period. And if we do accept a period, if that's what was next, then we pull in digits again, right? Because a floating point number could be something like that. So you'd want to pull in the 1, 2, and 3. Then accept run would stop. Then you check, see, okay, did we get a period? If so, then more digits. And the way this is written right now, someone could enter a number like this, and it would accept it. But that's okay, because we will be checking that eventually another way too. There's always a trade-off, like how much checking do you want to do in the Lexer versus the parser. Sometimes it doesn't matter. It probably takes more experience than I have to decide that intelligently. Okay, Okay, yeah, so we're going to have a special case here. So we think we have a number because we had a plus, minus, or a period at the start. But there is one case when we'll have a minus at the start when it's not a number. And that's our minus operator. Right? So we need to check for that. So we're going to check to see if the input the entirety of the input, right? So we've done all this accepting, but if all we got was a minus, right? We're taking the slice from the start to the end after all this accepting of things, and all we get is a minus. Then we know what we actually got was just an operator. The minus operator in this case. Otherwise, we should have an entire number now, and we can emit it as a constant. And then when we're done lexing a number, we can go back to the determined token state. And then the final case is if we get a operator, or we think we're at an operator because it hasn't been anything else, then we'll want to return a new function state, or new state function, lexop. We're going to use the except run again. And so we expect our operators to be upper or lowercase characters, or the plus, minus, divide, star symbols. And there could be numbers in it as well. So we'll give the plus, minus, divide, multiply. And then we'll do the whole alphabet. And then uppercase. And then the numbers. That should be everything. So this will just pull in however many characters there are in a row that match one of these. Right? So as soon as it hits white space, it'll stop, or a paren, it's going to stop. And then once it's done that, we can emit the operator and then go back to what determining the next token is. Oh, we need to return Lexer. Okay, what's left? Okay, begin Lexing. That's where we all started. So we've made a Lexer, but now we actually need to run it. So we're going to use a go routine. So the Lexer will now be running in a separate thread or separate go routine, going through this loop, going through all its states, and emitting tokens to the channel. And so what I'll probably now want to do is go on to parsing. So the parser will take just the tokens for now. Let me get an error because our parse function doesn't exist yet. But let's make it. Let's do func parse takes a, what is it, chan a token. Call it tokens. And that will return a node at some point. We'll just return nil for now. We're not going to have time to parse tonight, but we should have time to see if we have lexed things. So what we'll want to do is loop and get a token from the channel. So the OK variable tells us if if the channel's been closed and there are no more tokens available, we'll get not OK. Otherwise, we should be able to line. Print the value, put a comma between them. Is equal to. Okay, so that should print out our tokens if we get them. What's the problem here? Cannot use l.next. Oh, this should be index rune. Okay. So now all we need to do is tell our program to load up these things somehow. So we'll go back to evolvingpictures.go and go down to our main function. And then somewhere in here, we're going to get command line arguments. So we're going to pass in what file we want to load as a command line argument when we start the program. And you can get at those by calling os.args. This returns a slice of strings that is the command line arguments. And whenever you get args, all languages are like this. When you get the command line arguments, the first argument is always the program's name itself. So what you're really looking for is the second one. So we're going to see if we get a command line argument. Right, so if the length of this is greater than 1, because the first one's always the command itself, then we've got a command line argument. And we're going to want to do, we're going to want to load our thing from a file. So we'll say when you load things from a file, you typically get them as bytes. So we can use iutil again to read a file the same way we did to write one with a file name. and that will be the argument, the second argument, args of 1. So if we have an error, we will freak out. And then we can make our bytes a string by just casting the bytes to a string. And then we can say begin lexing our string. And then we will just return. Oh. Okay, I think that will fire it all off. Let's see what happens. We're going to pass it. Let me make sure I haven't added any unexpected stuff in here. Okay. So I'm running evolvingpictures.go and giving it the 1 command line argument, 1.apt. So let's see what we got. It looks like it might have worked. It kind of made it hard to read. So let's fix that. Let's just make this print instead of print line. All right, so it looks like we've got our tokens. Everything's broken up into a list. Our numbers are separate, parens are separate, and our function names are separate. But it also looks like this is running forever. So let's see why that's happening. Something is going forever and ever and ever. Let's go to the parser. Never got here, or it would have panicked. Oh, yeah, here's the problem. So when we're getting to end of file, we are not returning nil. So we need to return nil because that tells our loop right here to exit, which will then close the channel, and then things should actually stop. So let's give it a try. All right, there we go. So we got to the point where we had no more tokens and panicked, which is that's what we want for now. All right, we got done almost exactly at 9 o'clock. We have lexed our input. We've broken it up into an array of tokens. And surprisingly, this was the hard part. Turning this into our abstract picture tree again is pretty easy. And so next episode, we'll do that. And once we've turned it back into an abstract picture tree, then obviously it makes it, then we're ready to render it because we already know how to render those. Any questions about that, about the stuff today? There's some there's some new stuff today. We had the types that defined a new kind of function. We had a kind of weird recursive function loop here. So if there's any questions, let me know in chat. Or if you have questions about previous episodes, anything at all. By the way, this this case we have here, where we could potentially accept something like that as a number, we will catch this in the parser, because at some point we're going to take the value in our token, which will be this, and try to turn it into a floating point number, and we'll get an error at that point. So that's okay. All right, looks like no questions from chat. No homework stuff tonight because we're going to be going straight from this to the parser next time. And the parser won't take very long, so we'll have to think of maybe other things we could add to this tomorrow, like the second half of tomorrow. So if anyone has any ideas, feel free to type them in the chat or let me know on Twitter. There's lots of possibilities with this. So that is it for tonight. Thanks everyone for watching.